Now what we're going to do is two examples of determining an indefinite integral. So again, what you might want to do is pause the video at this time and try to see if you can do these two examples yourself. All right, so supposing that you paused the video and taken a little time to try them yourself, let's go ahead and see how you did. Remember that we're doing the chain rule for integration. And the idea here is we have a composite function, sine of x to the third plus 8, and we call that u for short. And we want to create the proper du on the outside of the sine. So, identifying that the u, the inner function for sine, is x to the third plus 8, let's just think what the derivative of that would be, what we want to have on the outside. So the derivative of that is 3x squared, technically dx. We don't have 3x squared on the outside, but we do have the x squared. So again, you could always adjust by a constant. So go ahead and writing this down again. We have the integral of sine of x to the third plus 8. And I'm going to write this on the outside with a little bit of space, x squared dx. And what we need to have here is the proper du, the proper derivative of that inner function. And remember that you could always adjust by a constant, because it's perfectly fine to multiply the entire integral by a constant. And again, remember, if you have to multiply by a variable, you cannot multiply by that variable on the outside. You have to use some other method for integration. So what we need to have here is a 3. So we multiply by the 3, and then remember to compensate by the reciprocal 1/3. And now we are ready to integrate. Remember that we're doing the derivative in reverse. So the integral of sine, remember, is the opposite of cosine. So we have negative 1/3, 1/3 was there, cosine of x to the third plus 8. And remember that the proper derivative that would have been produced in the chain rule is there. So we can simply write it as cosine of x to the third plus 8. And what do we always want to remember to include in an indefinite integral? A possible plus c. And remember that you can always check your indefinite integral by taking the derivative of that and seeing if it brings you back to where you started. Okay, for the second one, what we have here looks like it's going to be a natural log form, where what you have is you have a function on the bottom whose derivative is on the top. So again, if we're going to think of the denominator as our u, we think of u being equal to 1 plus 5x to the fourth, technically. And then we want to have the proper derivative of that. So the derivative of that would be, what do we get, 20x to the third dx, that's what we have. So now we're ready to set it up in order to find the integral. Let me go ahead and write that again. We'll write that in a form. So what we have is we have a 1 over u, 1 over 5x to the fourth, times, and we have x to the third dx. And what I'm going to do is I'm going to leave a little space there because we don't quite have the proper du there. But what we do have is we have at least the x to the third. And if you only have to adjust by a constant, you could always do that. Simply multiply by the missing constant, 20, provided that you compensate by multiplying by the reciprocal of that 20. And now we're ready to do the integral. This is the form 1 over u, 1 over a function, and then the derivative of the function is there. So we are doing the chain rule in reverse. So we have 1 over 20, and the derivative, or the integral of a 1 over u form would be the natural log of that form. So natural log of, we get technically the absolute value of 1 plus 5x to the fourth, plus c. And again, always remember your plus c. So this would end up being your final form. Note that 1 plus 5x to the fourth is always positive, so technically you would have absolute value. Although, had you written it without the absolute value, it would have been okay in this case because the 1 plus 5x to the fourth is always positive for all x's anyway. And again, as always, you could take the derivative of that final form and then see if it brings you back to the original function you were finding the integral of anyway.